Well, good evening, everyone. This is Dave. I assume you were probably listening to the chimes for my clock in the background there. So it's 6 o'clock, it's Thursday night, and so it must be time for us to have another session on our Intro to Cross Country. So tonight we're doing air data systems. Our overall schedule for this year. So tonight's air data systems, and in 2 weeks we'll start talking about portable gliding computers. The presentation download is hosted on the SSA webpage. It may take a couple of days after the session is done, but here's your information on how to get in there. You're using the members.ssa.org website, and it's on the News Resources Webinar subtab. And we really do want to thank the SSA for providing the webinar software and Frank for being our person behind the curtain for getting this up and running. Otherwise, we probably wouldn't be able to do all of this. You get Wings credit for this for the live class. So, and the folks that make that possible are Quay Snyder, Alice Palmer, and Mark Palmer. They are they're club members at Black Forest. They're also instructors. Quay is a designated examiner, and they're all members of the FAA safety team. So they're doing their best to make sure that we get this out and we make it available as credit for your wings training. We have some instructors from our club in the background. If you have questions, use the question mechanism and they'll answer as well as they can. If it's a larger audience kind of question, they may interrupt the presentation. If not, we will have questions and answers at the end. So if your question doesn't get answered immediately during the session, it probably will get addressed at the end. Some acknowledgments for the materials that I've got. The slides that have a light blue header on them were created originally by Richard Lancaster, and they ended up in the FAA's Soaring uh, handbook. So I've used that. Those are all copyrighted 2008 to Richard. Our purpose tonight is to gain an understanding of the air data systems in a glider, get a little greater insight into to variometers, and especially if you don't have particularly advanced equipment in the glider that you're using, uh, develop some tools that you could use in flight instead of going out and spending thousands of dollars for all new electronics in your glider. Now, one of the things that we need to talk about with this, the last session we discussed pre-flight planning and techniques to use that planning to reduce the stress of initial cross-country flight. And that was all the use of the tool, the glide plan, that was all targeted at pre-flight in order to set the stage so that when someone goes out, like when we were talking about the racetrack, they could say, well, if the winds are below this and I'm safe to fly with these winds, then here's the altitudes I need to use. And now I can concentrate on flying cross country, flying to the turn points, finding thermals, and I'm pretty sure I can always make it back. This time we're going to be talking about decision making and decision support in the cockpit. So what we're talking about tonight, except for the prep of the tools that I'll show you, is what you're working with in the cockpit. We're going to look at the instruments and how they work. We need to remember that they don't have to be absolutely accurate. Close enough. Close is usually good enough. Anything to the right of the decimal point, as I said last time, probably doesn't have any safety implication. So the real question revolves around the information block right here, and that is the information that you have good enough that you can make decisions? Okay. So the chain here is there's data, there's some transformation on the data that turns it into information, and information can be used to make decisions. Okay, off into a quick discussion of the atmosphere. So you can read this probably as fast as I could read it to you, so I'm just going to talk in the background while you guys read it. The sea level pressure, so if we start down here at sea level, and that's 1013 millibars, the standard millibar number for the pressure there, 2992 for the rest of that's what the world thinks in. We think in inches of mercury. So, and when you get up to about 18,000 feet, it drops roughly half. It will halve again by the time you get to 36,000 feet. But you notice the way that the curve is drawn, this is not linear. If you were to try to calculate it linearly, and if I looked at doing it for my home airfield, if it was a linear relationship, then the millibars at field elevation for Kelly Air Park, which is 7,000, roughly 7,000 feet. If you did it on a linear scale, it would come out and make it look like it was 7,700 feet. So it's a nonlinear relationship. Actually, we have our sea level standard number for Kelly is 781 millibars. So it's just off of, it's like I said, it's not linear. Standard atmospheric pressure. If you, the red numbers are the USA measurements, the blue numbers are the SI measurements. So standard barometric pressure, sea level 2992. They take it out to 4 decimal places. None of our instruments go that far. Temperatures at 59 degrees or 15 C, and then zero humidity. As you move off of those numbers, then the atmosphere, the density of the atmosphere changes away from the standard distribution. International standards. The real thing that I want to point out here, the 1013 millibars is roughly 14.7 psi. But one of the things I want to point out to you right here, this 1 millibar, notice how small of a psi number that is. Okay. Most of us can generate 5 psi if we seal our lips around a tube and blow hard. Okay. And I'll show you some numbers a little later about how few millibars it takes to put 60 knots on your airspeed indicator. So when I get there, I'll point it out to you. The key with this is don't blow into a tube that's connected to an instrument in your glider. You know, if you think you got a bee's nest in there, a wasp nest or something like that, don't hook it up to pressure air that you're still hooked up to an instrument. You'll blow the instrument out. The standard, the international standard, we do 2992 and 59 degrees, and then the international standard is 101.325 kilopascals at 15 degrees C, and the air density is defined as 1.1 or 1.225 kilograms per meter cubed. So the key with this, when you look at the equations for air density, when pressure decreases, the density decreases. So as you go up in altitude, the air density decreases. As the temperature increases, the density decreases. Now, the air density is going to determine our performance and our safety limits, but you know, air density is not something that we see directly on any of the instruments we have in the plane. But if you've got an engine, your performance decreases as you go up in altitude. Density altitude is the equivalent standard altitude for measured density. So when, like our airport, we sit at 7,000 feet above sea level, it's not unusual for us to have the local AWOS report our density altitude at 9,500, 9,700 feet. And all that's saying is that the density that it's measuring at the field elevation is the equivalent to what a standard atmosphere would be at 9,500 feet. Now, when you look at this, our sea level adjusted barometric pressure generally doesn't swing more than about 1.5 inches of mercury, plus or minus, or about 51 millibars, or about 5.1 kilopascals. So one of the things that when you look at this is, yeah, having high pressure move in or having a low move in, that can drive it. That can drive the barometric pressure up and down. But the thing that's really driving the density altitude is going to be temperature. That's the one that really drives the number change for the density altitude. Now, a quick little block diagram for the common air data instruments, the airspeed indicator, altimeter, and variometer. You can see the hookup depiction. Airspeed and altimeter are safety of flight. Variometer is a performance indicator. These are all precision instruments. The altimeter is the simplest from a mechanical point. The airspeed indicator is next. The Vario is simple, but in terms of understanding its behavior and what it can do for us is probably the most complex. All of these instruments measure pressure. The altimeter, it's pressure against a standard pressure. The airspeed is the relative pressure between two pressure sources, pitot and static. And then the variometer is the rate of change of pressure. Okay, so um, there's always a little bit of a flow involved between the elements inside the instruments, but what you're measuring is you're measuring pressure. Now, one of the things that we're going to, if you've sat through this before, I've added some stuff on our digital, everything's moving digital. A lot of our training gliders, and probably most of the gliders that everybody's flying, if you're not a contest or a hardcore cross-country pilot, you're working in an analog world. That's the real world, and the instruments that we're working with operate according to rules associated with mechanical models. As we have over the last, well, especially in the last 5 years, but as we've seen since the 302 was introduced, Cambridge 302 was introduced back in the 90s, where we started to move into the digital world. We convert the real world quantities into a virtual world, and then we operate on that virtual world with mathematical models. And I'll show you some of that this evening. Not going to go into great detail on it, but to give you a feel for how it works and how it's different from our mechanical heritage. So going into the altimeter. The altimeters are calibrated at sea level under standard atmospheric conditions. They have errors under all other conditions. So the sensing mechanism shown is the analog approach. So we have a device that's called an aneroid capsule. This is a sealed capsule, and it compresses as the air pressure increases around it, and it relaxes as the air pressure around it goes down. The static port comes in to the case, and then the capsule is inside the case. As the capsule shrinks or expands, it moves a gear train, and this is a grossly simplified gear train. It moves the gear train, and that's connected to the pointer. So when we are looking at it here, again, we've got static pressure, 1013, so we're talking, sea level. We take it up, let's take it up to 3,500 feet. The pressure drops to 890 millibar from 1013. The capsule expands, and that causes the pointer to move to indicate the new altitude. So the decrease in pressure has caused the capsule to expand, and the gear train causes it to move the needle. In general, with the aircraft moving through the atmosphere, what we're looking for is we're looking for locations on the airframe that are deep in the boundary layer, and they're clear of most of the aircraft's flow field. So you really wouldn't put although some manufacturers do, you wouldn't put it right up close to the nose. It might be back a little bit. So what we see with this is common locations for the static ports are Schempp for a long time and LS for a long time put static ports up here just at the front edge of the canopy. Schempp used to use static ports underneath the wing. A lot of companies put static ports back on the tail boom, especially if it was an aircraft that you're going to add a computer to because that gives you a real nice static location. And then we also end up with an alternate location for a static port on a boom that is connected to either horizontal or vertical tail. So those are where you could find it. The idea is to get the static port as much as possible out of the flow field of the aircraft and keep it buried in the boundary layer so that it's not really responding to the airflow over the aircraft. So here's one that just to give you an idea. Common static, the K-21 in its certification, its static ports for the altimeter that are for certification are the ones that are on the aft boom, about halfway back between the wing and the tail. Now, this is moving more towards the sensitive altimeter that we're used to using. So the one that we looked at before was just called an altimeter. When we add the adjustment for the local barometric pressure and the number we use is called the sea level adjusted barometric pressure, then it becomes sensitive to our current location and it can be used, to correspondingly report altitude between aircraft. So this was invented in roughly 1929. The gentleman that invented it was Paul Kalsman. That's why we end up calling this the Kalsman window, that little adjustment port and the adjustment knob. And what it does is it biases the display. In other words, it biases the pointers on the display uh, for the difference in the air pressure. So one of the things that you adjust is, like I said, it's adjusted to sea level adjusted barometric pressure. Barometric pressure drops roughly 1 inch per 1,000 feet above sea level. So an example, at Denver, when they have a sea level adjusted barometric pressure of 2992, the actual local reading will be something in the order of 24.92. But by setting the Kalsman window to the sea level adjusted pressure, then everybody that's adjusted to that local barometric pressure, sea level adjusted barometric pressure, is all working from a common reference. That's why the FAA tells you that you should be set to a barometric system that is, or barometric reading that's within 100 miles of your current location. Now, digital altimeters. They do pressure sensing not with an aneroid chamber. They do it with what's called a electromechanical system. And this is a pressure sensor that is reading absolute pressure. From there, that sensor uses a analog to digital converter to convert the analog pressure reading to a digital signal. Well, actually, it's a voltage, and then that's converted to a digital signal. It's transferred to a CPU somewhere, and then the altitude is calculated by measuring the atmospheric pressure and comparing it against the reference pressure, and then it displays the value. Now, the three-pointer antenna that we're most commonly used to using, we've got a long, thin pointer. That long, thin pointer is for 10,000ths of feet. We've got a short pointer, and that's thousands. And then we have a medium length pointer, and that's hundreds. Here's the window on the right for the Kalsman setting. So that one's set at 2992, and that's set by the knob over here at about the 8 o'clock position. So this altimeter is reading 10,180 feet with the barometric pressure set at 2992. On this particular design, the stripes down here are fully concealed once you get up past 15,000 feet. So it helps to disambiguate. It helps get rid of the ambiguity of the display. If those bars are all gone, then you're above 15,000 feet. So right now you can see that is partially hidden. As we look over at the digital altimeter, so the formula for digital altimeter or for it is you have a reference pressure minus your measured pressure, and then this is times 1,000 feet, and this is all done in U.S. measure. Now the reference pressure that you're using is your Kalsman setting, okay? And then you get a pressure. So if we had 2992 for our reference, our Kalsman setting, and we had 1435 was what was measured off of the little measurement instrument. Subtract that, multiply by 1,000, and we're sitting at 15,570 feet MSL. No, I didn't try it. This is the uh, Air Avionics ACD 57. I'm just using it as an example. One of its displays is an altimeter. By the way, it is a TSO certified altimeter, so you could put it in an aircraft with standard airworthiness if you needed to. And so in this one, your Kalsman settings right here, the units for your altitude, this one's reading in meters, and then the value is 1,284 meters, and you kind of a little scale over here to kind of help you set that so it's not just an abstract number, to help you bracket it. Pedostatic reference check. Okay. Advisory Circular 4313-1B, change 1. Yeah, I don't know if it's still change 1 by now. In Chapter 12, it talks about aircraft avionics systems, and Section 4 talks about pedostatic system checks. Okay. Now, one of the things you have to do is, you need to, whatever device, whatever altimeter you have, you'd check your manufacturer's documentation. But what this is doing is it's telling you what needs to be checked and that kind of thing. It tells you what, it does not tell you how. So it does not have the procedure in that portion of the advisory circular. So we're going to show you a static system check. The demonstration, we're using a water manometer. So it's a U-shaped tube. It's got colored water in it. Suction's going to be applied to the static system. You do it gently. You clamp and hold for 5 minutes. Any change in the reading of the altimeter indicates that there's a leak, and then you release gently. Leaks in the static system are the primary cause of altimeter problems, especially if you've got an older glider that's got the vinyl tubing in it. Um, you need to check it periodically because that vinyl will harden over time, and when it hardens, you can get leaks. The one thing you want to be careful of is if your altimeter is mounted to a moving part of the glider, for instance, the instrument panel lifts, you need to be careful when you're raising and lowering your canopy. I had a LAC 12, and it didn't use the lift struts, the airspring style lift struts that we're used to on the ones that we have the canopies that tip up from the front. It used a big over center fiberglass spring to lock it up. And then when you released the spring, if you weren't holding the canopy, it dropped on its own all the way down and slammed. Okay, inside these instruments are very small, very fine, very precise brass gears. Don't bang things around because at some point it's going to be a trip back to the shop in order to get your altimeter working again. Okay, this is a U-tube manometer. You can see right here that the tube, there's some blue dye in the water. I have a scale right here that measures the displacement of the water. I have a 60 cc syringe up here at the top that I can use to pull the suction. Okay. In this, when you're testing your altimeter through your static system, do not pressurize. 6.5 inches motion of water on here is 250 feet. So you want to be careful with it, but you do not pressurize your static system. The tube over here on the right with the bulb, that's for use when we're testing the pitot system. And then the tan tube over here goes over to the aircraft to connect into the aircraft. The other thing that you want to do is if you build one of these, you can find the drawings or descriptions of these if you want to have one around your club. Mine stays down at the club all the time. People use it to check their systems. Um, it's water with food coloring, just a couple of drops, and a couple of drops, not much more, of some, like Dawn dish soap, because what that does is that helps break down the surface tension of the end of the water so that you get a better reading. So, so I was working with this aircraft, and we're going to check the altimeter. So that's down here in the bottom right. And just a second. Come on. There we go. Every time I log into this system, I then have to go back and figure out how do I do this in order to run a video for you guys. And and no matter how hard I try to preset it up, I get here and then I go, how do I do this again? Okay, here we go. That's me stepping over the aft end of the fuselage. And you'll see the water go up on the paper. You can see the altimeter coming up. And then you would hold that position. And as long as the needle stays stationary for a period of time, then for the static system, that period of time is only a minute. If the loss is less than 100 feet in that minute, then the performance of the static system is considered to be satisfactory. So now let's work through this chain on the decision aid. So we fly day VFR. And so one of the questions is what's good enough? We're concerned with safety. The other one is, do we use the instrument or do we look outside? Okay, so if you're at 12,000 or 14 or 17.5, looking outside doesn't help you. You need the instrument. Whereas if you're coming back into your airfield, 1500 AGL and you're a half mile west of your field, you can probably see everything. You can probably make all of your decisions by looking outside. So when we're using the instrument, we have static atmospheric pressure and then the barometric reference pressure, which is what we set with the Colsman window. We convert that pressure data into altitude, and how it's done is it's then presented to us with a visual representation of altitude MSL. And our decision is, it's basically problem, no problem kind of thing. Are we at the proper altitude? Okay. All righty. Okay. Now we're going to go off and look at the airspeed indicator. When we look at airspeeds, we've got four values that we operate with around the aircraft. The indicated airspeed is the speed shown on the airspeed indicator. The calibrated airspeed is an airspeed indicated airspeed corrected for position installation error. The equivalent airspeed is the calibrated airspeed corrected for compressibility, and the true airspeed is the equivalent airspeed corrected for temperature and pressure altitude. Now, the relationships between these and the conversion from one to the other, you know, what I was taught when I was learning to fly, they called it iced tea. So indicated, calibrated, equivalent, and true. The compressibility issues start to show up around 100 knots. The airspeed altitude error can be roughly estimated by looking at about 2% less than true airspeed per 1,000 feet above sea level. So if you're 10,000 feet, and so you've got 10 times the 2%, so the difference between true airspeed and indicated airspeed could be in the range of about 20%. So if you're flying at 15,000 feet and standard atmosphere with an indicated airspeed of 100 knots, you're actually going 126 knots if you were looking at true airspeed. Now, why do we always stay with indicated airspeed? Because that's what all of the reference numbers on our airspeed indicator are in. They're not trying to make us use true airspeed. Remember, this is for safety of flight. Indicated airspeed is good enough for the vast majority of what we have to do in the cockpit. Now, in this case, this graphic, okay, vast majority of you are from the US, some of you are from international settings coming into these discussions, into these sessions. This airspeed indicator and its markings are based on CS22, which is the certification specifications for sailplanes and powered sailplanes in ESA world. The FAA references CS22 when it looks at trying to do certification for sailplanes or powered sailplanes in this country. It does not maintain a separate certification set of regulations. It defers to CS22. Now, our markings, especially those of us that have got gliders that came in through from Germany, the markings are to CS22, or if it's old enough, it was JAR 22, which morphed into CS22. Okay. So in this case, this is a 1.5 turn instrument. Winter made this real nice so that you had a good expanded scale. And then as you came around and started going faster and faster and faster, the numbers didn't need to be quite as far apart. So this let you really see the low end of your, down when you're around thermaling and then you're coming in for landing and that kind of thing. So and this one is marked in knots. The bottom of the white arc for CS22 is 1.1 VSO. So that's 1.1 times the stall speed in 1G flight in landing configuration. The bottom of the green arc is 1.1 on 1.1 VS1. So this is in your normal flight configuration for a 1G stall. Okay. In US markings, the bottom of the white arc is VSO, and in the bottom and the green arc is VS1. So you can see that there's already a difference there in the philosophy for laying out the instrument. The yellow triangle is your recommended approach speed. This is not your pattern speed. This is your no wind approach speed once you've got yourself stabilized on final. You might be flying, so this one's showing 45 knots. You might be flying 50 or 55 on downwind and slowing on base, and then slow to this once you've got yourself a stabilized approach on final. This number is supposed to be at max landing weight. And what you have to do is you have to check your aircraft's flight manual, because in some cases, the max landing weight does not include ballast. So you could have takeoff weight, a max gross for takeoff at 525 kilos, but you've got to drop your ballast in order to be able to fly this. So check your flight manual to be sure what that triangle means for your aircraft and for the configuration that you're flying it. Okay. The excuse me. Now uh, some like I say, some of the manuals will say approach speed at maximum weight without water ballast. The yellow triangle is generally under CS22. The yellow triangle is at 1.4 VSO. We've all trained in the US that, our target approach speed is 1.3 VSO. Okay. So again, check your flight manual as to what that means. Alrighty. So now we've got the white arc, so that's our flap operating range. And some airspeed indicators are marked with indicators. So for instance, in this one, it's saying L, so I'm assuming that might be landing. Um, you don't want to fly faster than, looks like 62 knots. Okay. And for your slightly less deployed flap, you don't want to go more than 68 knots, and you don't want to fly with positive flaps above 80 knots. Okay. Not all not all aircraft have their flap markings in the aircraft like that. And this is the operating range for positive flaps. Okay. The green arc is the normal operating range for the aircraft, and it terminates at, in CS22, it terminates at VRA, which is the rough air penetration speed. Okay, so this is your normal operating range. The yellow arc is your smooth air operating range. And then the red line is your never exceed. Okay. So with the bottom of the white arc at 1.4 VSO and the bottom of the green arc, so stall clean, 1.1 VS1, VY, the blue tag or the blue line, appears for powered gliders, and that's your VY speed. That's your best rate of climb, not your best angle, your best rate. And uh, and so that's the one that all the manufacturers. In fact, I haven't seen a powered glider handbook talk about VX. In the United States, you're flying a power plane, they talk about VX all the time. But that's VY, that's what the blue line represents. Okay, and then the top of the white arc is the top of positive flap extensions. So that's the max. Uh, and then, like I said, these are the other speeds down here are for partial flap extensions. Now, VNO, okay, it's marked. Uh, in the United States, we talk about the top of the green arc as VNO. In CS22 terms, it's called VRA. Okay. The key with this one is that's when the atmospheric conditions, gusts, the loads on the aircraft can exceed the structural limitation of the airframe. The and then you transition to the yellow arc and then to the red line. There are airspeeds that are not marked on the airspeed indicator. Uh, most gliders have a max speed to extend the landing gear and have a max speed once the landing gear is extended. Spoilers, there is a max speed to extend and a max speed when extended. Now, when I had my Ventus, my spoilers, you could use the spoilers all the way up to redline. Okay, so again, you need to check. The maneuvering airspeed, the one that we call VA in the United States, it's generally below the VNO or the VRA. It ties to accelerations that can be induced with control inputs. It depends on the mass of the aircraft. The lighter the aircraft, the lower the maneuvering speed because you can get it moving. You don't have the inertia of the additional weight dampening it. The so the key about the maneuvering speed, so you can't, you shouldn't be able to damage the aircraft with full control deflection. The VRA, the turbulent penetration speed, also can depend on the mass of the aircraft. So it can come, as you're lighter than, below your max takeoff weight, then that actually could come down a little bit, but nowhere do I find something that says how you're supposed to derate. The other one that's not going to show is your retractable. If you've got a retractable engine, the maximum speed to extend, the maximum speed with the engine operating, and the maximum speed with the engine not operating. So those are things that if you're flying with an aircraft that has a retractable engine, that you have to be aware of. And then the one that we all are aware of, and we'll talk more about it when we do the speed to fly session later on, is the performance numbers for minimum sync and best L over D, because those are condition related. Now let's talk a little bit about the red line. The red line comes in under the thing of what were the certification rules. If you've got an aircraft that has flexible structures, you could actually end up with multiple red lines depending on the how the plane was certified. In the U.S., a red line is based on the service ceiling, so that's an altitude adjusted to standard conditions, uh, and the gross number for it is that's the altitude adjusted for standard conditions in which the rate of climb drops to 100 feet per minute. So it's real easy to say what the service ceiling is for 172. But what's the service ceiling for a Schweitzer 134? No, I'm not going there. Now, in Europe, the it's valid. The red line is valid up to the altitude used for certification. That's commonly 3,000 meters, but again, check what your, check what it was for your aircraft. You may actually have to go look at the type certificate data sheet in order to find that number. Um, and what they do then is they provide a table that you use to derate the red line when you're above that altitude. So, if we're talking 3,000 meters, we're, I'm just rounding here, I'm not looking at a number, 10,000 feet, then if you're above that, then in this case, where it's showing the red line at 130 knots, if you're above that 3,000 meters, so let's say you're bombing along around 14,000 feet, your red line probably isn't 130 knots now. Now, if you want to be able to do this real quickly in your head, is you hold the true airspeed constant for the certification altitude, and then you compute the new number at 2% per thousand feet, that same 2% offset that we talked about before. One of the things that's become more common is they will have a table that they're telling you that you have to use in the cockpit near your airspeed indicator that gives you your altitude. Now, I've expanded this one out so it covers both meters and feet and kph and knots. So the so if you had a red line at 142 knots that was set at 2,000 meters during the certification, then you at 3,000 feet, your red line is decreased to 137 knots. At 10,000 feet, it's decreased to 92 knots. Okay. The So you have to keep this in mind. Some older gliders, for instance, my 1986 Ventus did not require this table, but my 1995 ASH 25 does, or A26, I'm sorry, not 25. My ASH 25, 26 does require a derating display, and this one is for a duodiscus. Now I'll show you a funny on my Ventus, my Ventus BT. I don't know at what altitude she was, the certification was done, but up to 16,000 feet, she's 135 knots. And at 19,000 feet, she only derates a couple of knots when you go from 16,000 feet up to 18,000 feet. And part of that was the structure that she was used. She was one of the early uh, carbon fiber wings that were designed to take advantage of carbon fiber, but was still, shall we say, somewhat overbuilt. She had a very stiff wing in her, so you didn't run into the flexibility problem. Okay, airspeed limitations. You can look at all of this. What it boils down to is there's a 10% margin between the V&E on the airspeed indicator and the maximum demonstrated flight speed that was done during flight test. Further, there's possibly a margin between the maximum demonstrated flight speed and the design maximum speed. Okay. So there are margins built into CS22 to where as long as you stay within the markings on the airspeed indicator, especially when you're talking about red line and you hit red line, the plane isn't going to immediately fall apart, but you can get into a realm of operation that, you know, is not a whole lot of fun. The one that comes up mostly is about flutter. So it's got to be free of flutter and divergence or control reversal all the way up to the design speed. And so the other one is that there's dampening available in the structure so that if you stop exciting it, it will dampen quickly. Okay. And then they have a whole list of subparagraphs on how you can show compliance. Now, the glider isn't going to fall apart if you hit V&E. However, flutter is a real consideration, and flutter can destroy the glider. There are folks that when I've talked to this earlier, uh, they go, well, that's ancient history. It's not ancient history. Flutter should not occur below V&E. Causes if you're getting flutter is if it's a design or construction problem, that should have been eliminated by the engineering and certification process. Where the problem comes in is if you've got an aircraft that's been damaged, some damage might not be apparent until the airframe flutters. Gordon McDonald does a whole bunch of technical work for the BGA, the British Gliding Association, and he's got videos out there that are fantastic. And one of them was a label that the owner reported to him that they were getting flutter when they were coming back on their final glide because they were pushing it up, but they were still below the maximum numbers, and they were getting a flutter. It turned out that the aircraft had had a ground loop at some point, and one of the formers back at the back of the aircraft, tying up into the vertical fin, had broken loose from the structure on the inside of the fuselage. What was really cute is I found out later, I watched the video when I was talking to a friend of mine in England and found out it was his label. Oh, how about that now? So, and the other one is, you know, your inspections don't necessarily find airframe damage. Let's say you had a minor ground loop, you look at it, nothing looks wrong, and you do a tap test with a quarter and you don't hear anything that sounds funny. Okay, let's go. The other one is that it may be improperly main control system components, stretching cables, not adjusted to the proper tension, those kind of things. The I had a case of flutter on my first fiberglass glider. The rudder was unbalanced. Now, in defense of the previous owners of the glider and the designer of the glider, at the time that plane was built back in the early to mid 70s, um, anything that had a red line below 120 knots, they didn't believe needed to have balanced controls. And it turned out that my rudder had been refinished and it was even more unbalanced than it had been when it came out of the factory. And I was bombing along about 10 knots under red line coming back in after a long cross country, hit some turbulence, and the rudder went into a flutter. I pulled back on the stick because flutter is the control surface, or the surface that's fluttering is extracting energy from the airspeed or the airstream, and you get rid of energy, you can get the flutter to stop, which is exactly what happened. Uh, Interestingly enough, it stopped at about 60 knots, which actually means the flutter speed that it could go into flutter at any speed above 60 knots, which was kind of scary. We actually ended up building a new rudder for it and had it properly balanced. But our quick fix for this was to balance this rudder, and it took an inordinate amount of lead in the leading edge of the bottom of the rudder to balance it. So I've got a couple of flutter examples for you that we'll take a look at. The first one we're going to look at is the prototype SB9 glider that the university system in Germany was using. Its first flight was in January of 1969. The wings were built in a full negative mold. So like they build gliders today, they had the negative mold. This wasn't a wet layup on the outside. The span was 22 meters um, with outer panels that were detachable. And they later shortened the outer panels by half a meter down to 21 meters. During the flight testing, there was some flutter phenomenon, which I've got the video I'm going to show you here in a second. The flutter problems were eliminated by using aileron mass balance. And then long after the SB9 was no longer being used, they pulled the wings over, put them on the SB10, and flew the wings for thousands of hours. So this is just this is just awesome. You may have seen this video, but so that just tells you that things can get rather interesting. Now, the next case, this one is interesting. Um, the purpose of this flight test was to validate the structural computer models that they were used in that were being used or phased in for the design phase. So the conditions of this flight were specifically set up to test if the aircraft would respond as the structural models, the computer models predicted. And by the way, it did. So this is a DG300 modified to 17-meter span. And the additional span was not added at the tips. It was added by putting in plugs at the wing root. So they beefed it up. The airspeed was somewhere between 87 and 93 miles an hour. Um, they knew they knew how to stimulate it, and they knew how they expected it to behave. So this one is kind of interesting. The key with this is when they reduce the airspeed by pulling back on the stick without hindering the sideways motion of the sticks, because you're going to see in this that it's clearly in the ailerons. The flutter oscillations stop, but only when you get down to a much lower speed than where you triggered it. And that speed where it stops is the actual flutter speed of the plane. The flutter will start when this airspeed is exceeded, and the right disturbance influences the plane. So in my glider's case, it was the turbulence that I hit. When I was in smooth air, it was just fine. So
es geht los. 150, 148, 145, 142, 140, 135, 130.
So, how would you have liked to have been the test pilot in that, doing that intentionally? Alrighty. The next one, this one I think is interesting. Many of you may have had the opportunity to see the Perlin 2 aircraft when it was at the convention in Reno a couple of conventions back. And one of the things that they did with her is she was being built with models that they were extending to a maximum altitude of 90,000 feet above sea level. So part of what they did is they put some exciters in the structure so that they could excite the aircraft in the air at reduced uh, air pressure, air densities, in order to validate the equations that they used in their design software. So they put vibrating wings in the wingtip spar. They had accelerometers in the wing. The small monitor that you see on the screen, the horizontal axis is the frequency of the disturbance. So that looks like it goes anywhere from 0 hertz up to about 27 or 28 hertz or cycles per second, depending on how you like to hear that term. And then the top graph is a bending measurement, how much it's bending, and the bottom graph on that little chart is the twisting within it. They had similar displays inside both cockpits. This is one that's sitting on a bench, obviously. They had similar displays inside the cockpits so that when they did it in flight, that both pilots could observe the data. And just in case, they also telemetried the data down while they were flying. So while it was in flight. But this is the kind of thing that they end up doing. Again, this is a validation exercise for the aircraft that the models they used to design it, that it behaved the way they expected it to. So Flutter is not an old wives' tale, and at least two of these were specifically to test software that was used to design the aircraft. But when you're playing at the extremes of your airspeed indicator, you're a test pilot, and it's up to you whether you really want to play there. Okay, just a second. Did I go? No. Okay, I thought I double clicked. All right. So airspeed indicators are calibrated at sea level. There's errors above that under all other conditions. You can see we have a pitot tube coming into a capsule with a diaphragm. So this capsule diaphragm connecting to the pitot replaces the aneroid chamber that we saw in the altimeter. And then we bring in the static pressure into the case on the instrument. And so now the expansion and contraction of this is corresponding to the dynamic pressure, and it's being referenced against the static pressure. Pitot tubes are often mounted in the nose. And It doesn't have to be a straight tube all the way back to the uh, airspeed indicator. Some aircraft they have a closed chamber, and because we're measuring pressure, not flow, and so when that chamber comes up to pressure, that's what they're measuring it against. There is an alternative location that shows up on the vertical, possibly on the vertical and the horizontal tail, depending on the kind of probes you have mounted back there. So again, we're talking pressure, not flow. The uh, so you can read this. This will show you here's where it's sitting still. There's nothing coming in on the pitot tube, and where the static is coming in here on the side at 30 knots. The pressure at 30 knots. If static just sitting there on a standard day was 1013 millibar, 30 knots is 1015 millibar. 60 knots is 1019 millibar. So notice that this relationship, as well as the altitude relationship for the altimeter, is nonlinear. Some of the uh, Shimp-Herf models have problems with the way when they went back and added the nose hook to the venison discus at some point, then while you're connected to your tow plane, if you use a wiffle ball on the end of the rope, that can interfere with the airspeed reading while you're on tow. Okay. We'll talk about the digital version of this. We're talking about the analog version right now. We'll talk about the digital version down on about 5 slides. But what I want to point out to you, okay, remember how small a 1 millibar was? So from 13 millibar to 19 millibar, so 6 millibar of pressure, and remember that was 0.01, it was way down there on the PSI. So if you put your mouth on that pitot tube and blow, you put 5 PSI in there, you know, you can damage something. Don't put pressurized air in on that line, or not that kind of pressurized air. Okay. So the plumbing, again, we're looking at a K21, got the pitot in the nose, static back here with the instrument in the cockpit. The So in this case, now it's showing what I was describing earlier. So you've got with equal pressure, you've got a size here, and then with the dynamic pressure pushing on it, the chamber expands, and then it goes over into moves the needle. Digital airspeed sensing. Again, we're back to the little pressure sensors. There will be 2 sensors. So you've got one for pitot and one for static. There's all kinds of configurations for this hardware, but there will be 2 sensors. The sensor package itself may be doing a whole lot of work for you, but let's just leave it as 2 sensors. So in this case, we get the A to D converter that's converting both measurements, and then we get it over to the CPU, and then we're going to calculate the airspeed by measuring using the dynamic measure and the static measure, and then displaying the value. The static references, again, we're talking about 43131B. So we looked at static system a moment ago. We're going to look at the pitot system here in just a moment. And then here is for the digital airspeed, here's the formula. So we've got a pitot measure, a static measure. If you run it through uh, the formula works in pascals and meters per second, but if I convert the meters per second for uh, that 6 millibar difference, it comes out to 60.8 knots calculated. And no, I didn't try to make it match the LX Nav ADI. This is their digital airspeed indicator with a digital altimeter. And if you configure it, you can have a total energy vario over here on the right-hand side. So you can have this one instrument replace 3 instruments in your panel and gain space for 2 more. So airspeed, we're going to take a look at the demonstration for that. What we're looking for is we're looking for leaks and we're looking for clogs. So we've got the water manometer again. This time, instead of a vacuum, we're going to apply, or a suction, we're going to apply pressure gently. The description of the process is you seal it for 5 minutes and then you release it gently. And as long as it holds for 5 minutes, that's fine. If you hold it for 10 and it drifted, you met the 5-minute requirement. Again, here's the manometer. This time we don't have the 60 cc syringe. The white card has the chart on it, the airspeed chart. And so this is the same manometer that we had before. And in this case, we're going to be working with the airspeed indicator in the top of the panel. And the bulb I'm using is just the pressure bulb off of a blood pressure tester. So you bring it up gently. And basically, you don't want to go all the way to the top of the travel, but you do want to, for the most part, you want to go to the top of the yellow arc. In this case, I took it to 140 knots. You can see over on the left-hand side the fluid coming up in the tube on the manometer. And the numbers on the right-hand side of that card are in airspeed in knots. And you can clearly see by the spacing of the numbers there, the nonlinear relationship between the pressure and the airspeed. So that's sitting right at 140 knots. And now I'm bleeding it back down. Doing these kinds of tests are especially useful when you're working with an older aircraft. One of the members of our club picked up a PIC 20D that had been sitting in its trailer for years and years and years. And he went to fly it and he was rolling on the runway on tow and his airspeed indicator didn't come to life. So he released, rolled it off to the side, and then we put the manometer on it and found out that there were leaks everywhere and all that kind of thing. But we also found out if you've got Blaniks, because remember the Blaniks, even the L-23s are getting kind of long in the tooth, and they used a natural rubber tubing with a kind of a cotton mesh on the outside, a cotton sleeve on the outside of it. And they end up deteriorating and developing cracks, especially where there are bends. So we found out that our Blaniks airspeed system had problems by using the manometer. So I find, like I say, I built this to test my own aircraft, and then I made it available as a tool for the club, and so it lives down in one of the tool rooms at the club. So, all right, so now airspeed decision aid. Again, we're looking at this thing. You know, can I tell? Do I have to use the instrument? Well, if I'm at 12 or 14 or 17.5, probably. I get down low and I'm in the round out at the bottom of the pattern or bottom of the approach. I'm probably watching a whole lot of things and only only slightly looking at the airspeed indicator. But we have static atmospheric pressure, dynamic atmospheric pressure, and remember that dynamic also includes static. So basically, when we compare the two, we're canceling it out and just leaving the dynamic pressure, the pitot pressure. We convert the information to airspeed with a visual presentation, and again, we come back over here to problem, no problem. Am I on my proper airspeed? Okay, now one of the things with your aircraft, even if you've got one that's experimental, if you didn't build it, it came in from Europe or South Africa or wherever. Um, since this is in the national airspace system, the primary altitude and airspeed indicators must derive from the approved pitot and static sources. And in general, you'll find that your operating limitations that were issued with your aircraft when it came into this country will require you to maintain it to the standards of the original manufacturer, even though you have some flavor of an experimental airworthiness certificate. Generally, the operating procedures will require you to maintain the aircraft in the configuration of that the manufacturer, or in a manner that the manufacturer specifies. All right. Let's jump over to variometers. Yeah, it's funny. This is an extremely simple instrument. Um, basically it looks like it's almost a variation of the altimeter, really. We have uncompensated variometers. We have total energy compensated variometers. We have netto or air mass measuring variometers, and we have relative netto or super netto variometers. Okay, and we'll work through this. When we have this is a rate of change instrument. Okay, whereas the others were measuring the pressure, this is going to measure the rate of change in the pressure. And the way it does it is where we had the pitot tube before, it's going to put a capacity, and that capacity is going to connect to the chamber, to the capsule. Only this time it's got a calibrated leak. And we know how much flow, or we know how much it can flow with pressure change between the two sides. We bring static pressure in over here. Later on, when it becomes total energy, we bring in the total energy probe. Okay, so don't worry about that. But this is a rate of change. So the capacity becomes an analog stored atmospheric pressure reference. This is what the pressure was some time ago in seconds. Okay. Depending on the size of the capillary hole, this could be a couple of seconds, it could be 10 or 20 seconds. Okay. And if you look at this properly, you think about it a little bit, an averager is really just a very slow variometer where this time constant for being able to change is 20 to 30 seconds is how long this memory is maintained. When we look at the digital variometer, we're back to a sensor does convert the voltage gets converted to a signal that's sent to the CPU, and then we're using atmospheric pressure. If the software is good enough, you don't need a capacity because you're measuring absolute pressure, and it's all done. And now it's all done in the software in the CPU. So if you've got memory, the memory is the process is the memory for the software that's running. Variometers, simple variometer, capacities to the variometer, and using the same static port that we're using uh, for our airspeed and for our altimeter. Uncompensated variometer, so it's 900. Everything's, we're flying straight and level at 3,000 feet. We went up to, we're now at 3,500 feet. We're climbing from 3,000 to 4,000. The pressure out here has decreased. The pressure here is decreasing through this little leak, and that moves the needle. So in this case, We've got the stored pressure information. We've got the current static pressure information. We're going to convert that into a direction, so climbing or sinking, and rate of change. We get a visual representation. So now, the question is the glider rising or sinking? Or the other one is if we're established in a thermal, then this becomes what is the quality of the thermal? Is this a 3 knot thermal, a 4 knot thermal, a 5 knot, or is it 3 knots on one side and five on the other? That kind of thing. And again, in the digital systems, the stored atmospheric pressure is a value in the processor's memory, so no capacity required. Now, total energy. So the goal here is if you got a simple variometer, we can fake the variometer out and make it think we're climbing by our, what we do with the control stick. So the idea here is that if we are cruising along at 80 knots, we pull back on the stick and we now find ourselves at, 3,100 feet and 50 knots because we use some of our airspeed and changed it for altitude. We pulled back on the stick, but, our climb was purely by the exchange of airspeed. Okay. So that's a stick thermal. All right. We didn't climb in a thermal. So now when we look at this, what we're looking at is we have the energy. So we have potential energy. So this is, the energy that it's holding just because of, you know, where it is. We have kinetic energy, which is the energy by virtue of being in motion. And then total energy is the sums of all kinds of energy, all the kinds of energy that a body can have. So if we pull this over to glider terminology, our potential energy is proportional to our altitude. Our kinetic energy is proportional to the square of the airspeed, and our total is the altitude combined with the airspeed. Okay. Now you have to remember that the exchange of speed for altitude is always a lossy conversion. It's not a one-to-one conversion. The Vario is going to show a rate of change for altitude. You pull up and lift. So we're interested in the rate of change, so the altitude gain while we're slowing. We're interested in seeing the change due to the atmosphere, the gain because of the lift. Okay. So there needs to be some way to factor airspeed into the Vario display to get rid of this thing of this energy change was because we changed airspeed. We've got to come up with a way to get that component out of the instrument. And so what we end up doing is we end up, instead of plumbing the variometer to the static system right here, we bring it back and we put it onto a TE probe, a total energy probe. The secret of the total energy probe is it's a sealed tube with an opening on the back side of the tube. The size and placement of the opening is important, but basically what's going to happen here is it's going to give us a pressure signal that is very similar to negative air. It's going to be the dynamic pressure, but instead of a positive number for airspeed, it's going to have a negative approximation of airspeed. So then what you're seeing the static pressure change with the airspeed component subtracted out of it. Now, you may see gliders that have a taped hole on the top of the fuselage. So it's used to be common before we started having aircraft with the plumbing built into the vertical fin that folks would come in and mount a TE probe here. The one that was most common in the United States, I think, was called a Nix tube. It went up and then had a slight bend in it. And that was easy because it could be done in the turtle deck area of the glider. So in this case, what we end up with is we can also approximate total energy especially in some of the gliders that come out of Poland. You'll see a brown diaphragm, and it's connected into the plumbing behind the panel between the in where the capacity and the where the lines come in. I don't remember if it goes in the static line or if it goes in coming out of the capacity, but that diaphragm does some of the same kind of work. So you'll see that the club's PW5, I don't know if it still has it in there, but our club's PW5 had that in it. So working with this, basically we get uh, negative dynamic pressure. So we still get all of the static pressure, but now instead of a positive number for the airspeed component, we get a negative number for the airspeed component. It's not exactly negative airspeed, but it's close enough. So when we look at total energy, uh, again, we've got a sensor. We're sending it over. We're using atmospheric pressure. Um, so we're using the static. And on many digital variometers, if you're not using or no, anyway, forget it. That's a later one. So the capacity is not required. The TE probe is optional. So the TE probe can be plugged into the TE probe port on the back of the variometer. So and then the electronic compensation, if it can handle total energy, then you probably have electronic compensation available so that uh, you don't have to have a probe. You could do it just if you had airspeed and static or pitot and static on the back of the variometer, then you could use those two quantities and compute the electronic compensation could then be applied to it without having to have a TE probe. That's why I say it's optional. But if you've got the instrument that's got the three probes or three ports on the back, pitot, static, and total energy, you connect the total energy probe to the total energy port on the back. If you're going for electronic compensation, what you do is you jump so that static feeds both the static port and the total energy port, and then you set the electronic compensation number in the settings to a value that tells the variometer that it's using electronic compensation rather than probe compensation. So it's you can mix and match this, but it's the configuration of the plumbing on the back of the instrument, and then you have to match that with the processing in the instrument. So the TE probe measures or TE vario measures the variation of the glider's total energy. So it's the rate of gain or loss corrected for the glider's airspeed. The actual change, excuse me, it's the actual change rather than just the change from exchanging speed and altitude. Okay. It will indicate the actual rate of sink corresponding to the actual velocity and according to the glider's performance polar. So for instance, if you're flying at 82 knots in calm air, it, I think this is from my Ventus, I should expect to see 4 knots down indicated. Okay. If you're circling in a constant airspeed, the TE and uncompensated varios will have basically the same indication. In other words, when you slow down and you're in the thermal and you're holding a constant airspeed, then the airspeed doesn't change, even though the direction that you're flying changes because you're in a circle. But now you're getting the quality indicator of, is this a 3 knot thermal, a 4 knot thermal? Is it better on that side than this side? So we start with the stored pressure reference, negative dynamic pressure, convert those so that we get direction and rate of change, get a visual representation, and now we're looking at it, is it rising or sinking? And if we're slow enough, we slowed it down now and we're thermaling, what's the quality of the thermal? Now, what this is really doing for you is that if you were to pull back on the stick, your Vario is not going to go wee, 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 and say, oh, I've got lots of lift because, that's not what you're doing. You just traded airspeed for altitude. Now, netto variometer. This adjusts the sink rate of the glider uh, at a given speed. And so, and it also might be able to adjust for water ballast. So what the netto is doing is it's showing the air mass movement. And I can really try to explain this, but you're better off taking those notes, getting the slide deck, and sitting there and looking at it for a while. It will eventually make sense. But basically, I'll just do the top line. If I'm flying at 60 knots, this is based off of a Ventus BT Polar. Your sync rate is minus 1.4, and the Vario reading is showing uh, minus 6.4. The netto reading, in other words, what's the air mass doing, is going down at 5, minus 5. Okay, this is if you're in sinking air. If you're in neutral air, then it subtracts out the 1.4, and the netto reading says the air mass is not moving. The number's 0. Okay. If you're in rising air, then the TE is going to show 3.6 because it's subtracted out. Uh, the TE, and so the netto reading is 5. Okay. So what it's doing is it's subtracting, or it's taking the glider's polar away and telling you what the air is doing around you. So one of the ways that you could do this, you could create a little chart that gives you uh, those three numbers. I had minus 5, 0, and plus 5. Or in this case, you could set it for air mass 0. And if uh, in this case, you know that if you're showing 1.4, that the air mass is not doing, the air mass is not moving up or down. So this is a nice workaround if you don't have the electronics. You can build these tables. In the variometer, you can most of the electronic variometers anymore have a netto function in them. And basically what happens is if you have the sailplane polar, if you can get the polar in there either by putting in uh, the coefficients for the quadratic equation, or there's three different ways of representing the polar, so don't worry about the specifics. But if whichever way that the variometer wants to use, you get your glider's polar in there using that method, and then this will be telling you, the red needle up here will be telling you what the air mass is doing, and adjusting what the what's happening by getting rid of the glider's portion, whether it's plus or minus, and tell you what the air mass is doing. Now, that's nice to have. And there was a period of time when being able to have this data was the cat's meow, I guess, is, I want to go back to an old MASH TV show reference. Okay, so here's our decision aid. So we've got the static atmospheric pressure, the negative dynamic pressure. Uh, we've got airspeed. We've got the glider polar, and we may even have the glider mass. We're going to convert for direction and rate of change. And we're also going to, if we've got a TE variable, then we're going to get rid of the airspeed components. And so we get a visual representation of the air mass motion around the glider. If we're thermaling, we're back to getting a quality of the thermal. Okay, so how's the air mass moving around us? And if we're in a thermal, we've got a good indication of the quality of the thermal. The next one, the first time I saw this was on a Cambridge 302. And I think the netto was also on the Cambridge 302, but once I found out that there was such a thing as a relative netto. So this indicates the vertical speed of the glider if uh, we slowed to thermaling speed. In other words, we're gonna be looking at the thermaling speed circling polar for the glider. So basically, it's the netto reading minus the glider's minimum sync. And when you're thermaling, you're back to, but you get down to that speed, you're back to it's just behaving, giving you a quality indication. This one's a horrible slide. I actually, before I put an electronic vario that could do relative netto in my glider, I actually flew with a chart like this laminated to help me understand how the air mass was working around me. And so again, if you want to try to figure out, go back and reverse engineer this, pull the slide deck down, pick a number, pick a polar. Like I say, this one's based off of a Venice polar, um, and enjoy yourself. But yeah, I actually flew with this kind of a chart in my cockpit. And then this was one showing uh, 2 knots thermal sink rate. Now, you can pull all that down to something that looks like this, and it will, this is just an extraction from the previous chart. I think you can understand why I decided I wanted to, once I could afford having an electronic vario. And by the way, a 302 is still an excellent vario. It doesn't do everything that a vario that was designed and built in the last 5 years will do, but if you can find one, the only problem is that basically they're unmaintainable now because the parts have been exhausted and the person that was taking care of them. But if you got one and you get it cheap and it works for a while, congratulations. It does all of this stuff for you. So again, now the number that you're being shown while you're in cruise is the estimate of what the circling climb rate would be. So again, here's all the number, here's all the sources of all the types of data that feed into this. Here's the transformations. Here's the kind of information. So we have a presentation of the potential climb rate, running straight and level. That gives you an idea of whether or not it's worth stopping for the thermal. If you're thermaling, then it's back to giving you the quality of the thermal. Um, so now one of the thing, yeah, anyway, okay. So now going beyond total energy. Total energy is the foundation of netto and relative netto, but it has a flaw. It cannot differentiate between lift and a non-vertical gust in the atmosphere. So if there's a horizontal gust, you feel the turbulence and the variometer, because it changed the airflow over the total energy probe, the variometer responds, but it's not really lift, it's just a perturbation in the atmosphere. So since we've got an embedded computer in our digital variometer, how about we take advantage of it by adding some additional hardware? So if we add a 6 degree of freedom inertial measurement unit, okay, so there's a 3-axis accelerometer, an acceleration sensor, pitch, roll, and yaw, 1, 2, 3. And that's going to give a direction and magnitude value. And then we have a 3-axis gyro sensor, which I'm translating it away from X, Y, and Z coordinates into pitch, roll, and yaw, so that you're thinking about it from a glider's perspective. So that's number 4, number 5, and number 6. That's the 6 degrees of freedom that are being measured. And then in this case, we get direction and rate. So this is how hard we got pushed, and this is how fast we're being put. This is how fast we're changing. If I take that, bring it in, I can put software in the Vario or put software in the computer that you connect the Vario to. I can detect the motion that is not related to lift, so I can determine that this gust is not contributing to lift. All it's doing is making my Vario scream at me. So then I can get an indication that the felt acceleration is a gust, not lift. Okay. What that does is maybe it can be applied to the Vario needle, which is the red one I'm highlighting right here, and stop it from screaming up here at 4 knots when it's really only 1.5. Okay. Or the other possibility is that I could give you a second needle that was giving you an indication that what this guy was seeing, what the red needle was seeing up here at 3.5 knots, really wasn't 3.5 knots. Give you another needle that works in conjunction with the red needle. Okay, what I'm describing is a gross oversimplification of some of the Hawk processing in the LXNav devices. But what I want to point out is that adding this inertial measurement unit, and they come commonly as either 3 degree, 6 degree, or 9 degree. The 9 degree adds a magnetometer, so a mechanism to get a magnetic compass if you needed it or wanted it. But what I'm pointing out is there is something that could be added to our variometer that takes it beyond total energy and moves it into was that bump for real? And which I think is that's a really neat capability. So, questions?
Thanks, Dave. That was great. I think one of the biggest questions we got a few times tonight to provide some clarity is the nothing really actually to do with the conversation of the scenarios here, but the email links and how we sign up for the sessions every 2 weeks.
Oh, okay. Um, if you've got a Wings account, use that email, your Wings account email, use that email when you sign up for the sessions. And then that makes it easier for our folks that are running around in the background when they submit for Wings credit, because that's your email that you use for Wings is the key. Um, the
One question, I've been going back and forth with Alice on this. This is Frank. All of these require registration individually. Some people, I think, registered for the first one thought they were signing up for the whole series. Zoom requires a registration for each one of these. Part of that has to do with the Wings credit, but it also gives us a measure of how we're reaching people either via the website or social media. There is a registration link on the SSA calendar on www.ssa.org for each webinar. There is a link in Coffee Time as it gets emailed to members that takes them to that calendar link. But it didn't explicitly say that you have to register for each webinar in turn. So if you do that, the Zoom program is supposed to email you 2 or 3 times with reminders, including one hour before the webinar. So that's with that link. That'll come out at the time you register, you get the link, and then you're supposed to get 3 reminders.
Thank you, Frank. I hadn't thought that the question was in that direction, but that also makes a whole lot of sense that we've got to register for every one of these sessions.
Right, and then if they should register with their where they're signed up with the FAA safety email, using that one to get the credit. If they inadvertently sign up with the wrong email, they've got to just email webmaster@ssa.org, and we'll take care of making sure we get the right email.
Frank, can I jump in here? It's Alice. The best thing would be to put a note in the question box with the correct Wings email, because I usually do Wings credits the day after, and we might not catch it in time unless they let us know, like at the time of the webinar, that they're using a different email address.
Perfect. And we do have one last minute question here. This is a good one. Chris wants to know, do digital Varios use aneroids?
No, they're using an electronic sensor that reads absolute pressure. So you don't, it's pressure against a sensor uh, that then is converted to a voltage, which then is converted to digital data.
Perfect. Those are all the questions that we have, Dave.
All righty. Well, next time, same bat channel, same bat time, February 12th, and we'll be talking about portable gliding computers. So the handhelds that people are taking into their cockpits and using them. Y'all have a good one, and thanks for being here.